All right, let's dive right into this. Welcome to today's explainer, where we're going to embark on what I like to call the code breaker's journey. You know, the digital world you interact with every single day, the text you're reading, the images you're seeing, the apps you use, it is all built on this secret underlying fabric of number systems. It's like a giant puzzle, and today, you become the code breaker. We are going to peel back the layers of these invisible translations and see exactly how our machines actually think.
Now, if that sounds like a ton of math, hey, don't worry. We're unlocking this one manageable step at a time. Here's our roadmap for today. First up, cracking the hexadecimal code. 2, the binary translation shortcut. 3, grouping for octal conversions. 4, conquering the fractional frontier. And finally, number 5, testing your decoding skills.
Okay, let's jump into part 1, cracking the hexadecimal code, unpacking the code to base 10.
So base 10, that's just the standard decimal system we use every single day. But hexadecimal, that is base 16, and it's a way denser way for computers to pack information. So how do we translate from base 16 back into our normal base 10? Well, the fundamental rule here relies on positional weight. Step 1, we simply separate the hex digits. Step 2, we multiply each digit by increasing powers of 16. And we do this starting from the right side and moving to the left. And finally, step 3, we just add all those individual results together. It's essentially our guide to systematically unpacking a complex cipher.
Let's see this process in action, because it is pretty wild how fast this scales. Say our hexadecimal code is A, B, C, D, E, F. Since it's base 16, the letters A through F actually represent the values 10 through 15. Now look at how quickly this scales up. Starting from the right, the letter F, which represents 15, is multiplied by 16 to the power of 0. That's just 15. But by the time we reach A all the way on the far left, we're multiplying its value of 10 by 16 to the power of 5. When we add all those results together down at the bottom, the seemingly simple 6-letter code ABCDEF translates into a massive decimal number of over 11 million, specifically 11,259,375. It beautifully illustrates just how densely packed these hexadecimal codes really are.
Moving right along to part 2, the binary translation shortcut, bypassing decimal.
All right, get ready for a little plot twist here. What if we want to translate straight into machine code, binary, without all that heavy decimal multiplication? Well, we have 2 options. Option 1 is the long way. We take our hex number, do the heavy math we just learned to convert it to decimal, and then do even more math to convert that decimal into binary. Honestly, it's incredibly tedious. But look at option 2, the direct way. We take the hexadecimal input and convert each individual hex digit directly into a 4-bit binary output. It is an absolutely elegant, super efficient bypass.
Consider this table your absolute master key. Literally, your ultimate code-breaking cheat sheet. It maps decimal, hexadecimal, octal, and binary directly to one another. Notice how every single hexadecimal digit, from 0 all the way to F, matches up perfectly with a very specific 4-bit binary sequence. With this key in your back pocket, decoding becomes nearly instantaneous.
So let's actually put that master key to work. Look at how crazy simple it is to decode the hexadecimal number 9A into binary. We just pull the blocks directly from our table. The hex digit 9 translates instantly to 1001. The hex digit A translates to 1010. We simply snap those 2 blocks together and boom, our result is 1001, 1010 in base 2 binary. 0 massive multiplication required.
That takes us to part 3, grouping for octal conversions, repacking the bits.
Now that we know how to bypass the heavy math to get into binary, we can actually use that new binary knowledge as a stepping stone for our next cipher, octal, which is base 8. First, we convert our hexadecimal number directly to binary exactly like we just practiced. But here's the clever part in step 2. We take that long string of binary, starting from the right, and form it into smaller groups of 3 bits. Think of it like taking items out of one giant box and repacking them tightly into smaller, specific-sized boxes of 3. Then, step 3, we just match each 3-bit group to its octal equivalent, using our master key.
The crucial takeaway here is how this shift in grouping just magically yields our base 8 translation. Let's walk through an example, 3DC in hexadecimal. First, we pull our 4-bit binary blocks for 3, D, and C. That gives us a long string, 001111011100. Now, we regroup them into boxes of 3 bits each. So, reading from left to right on our newly grouped bits, we get 001, 111, 011, and 100. Checking our master key table, those translate to 1, 7, 3, and 4. And just like that, hexadecimal 3DC magically repacks into octal 1734.
All right, part 4. Conquering the fractional frontier, beyond whole numbers.
Just when you thought you had this whole code-breaking thing totally mastered, right? We're introducing a new frontier, decimal points and fractions. To convert a fractional decimal number into another base, our approach flips. I want you to contrast the dividing and grouping techniques we use for whole numbers with this new multiplying and extracting method. Basically, we multiply just the fractional part by our target base, like 2 for binary. Then we extract the integer part of that result. We take whatever fraction is left over, multiply it by the base again, and we keep continuing this process until the fraction becomes 0 or we hit our desired precision. Finally, we read those extracted integers from top to bottom.
To ground these complex rules in reality, let's tackle a specific fractional challenge pulled directly from our source material. We need to convert the base 10 number 25.625 into binary.
The trick here? We just split the problem in two, divide and conquer, handling the integer and the fraction separately before reuniting them. Step 1, we convert the whole number, 25, into binary using standard methods, which gives us 11011. Now for step 2, the fraction. We take 0.625 and multiply it by our target base, 2. That equals 1.25. We extract the 1 and keep the 0.25. We multiply 0.25 by 2, getting 0.5. Extract the 0, keep the 0.5. Multiply 0.5 by 2 and we get exactly 1.0. We extract the 1, and since our remaining fraction is now 0, we stop. Reading top to bottom, our fractional binary is 101. Finally, step 3, reunite them, 11011.101.
Now, what if we need to reverse this whole process? Say, converting a binary fraction back into a decimal number. The positional weight rule still applies. It simply shifts into the negative past the decimal point. The first bit after the point has a weight of the base to the power of -1. The next is to the power of -2, and so on. You calculate those specific values and sum them up, just exactly like we did with whole numbers.
Which brings us to our final section, part 5, testing your decoding skills, the final challenge.
All right, you've absorbed the rules, you've got your master key techniques, and you just conquered the fractional frontier. So now it is time for you to act as the ultimate digital detective with a class activity pulled right from our source material. Your challenge: convert the hexadecimal number 9AF1 into a base 10 decimal number. Remember our very first lesson on positional weight and multiplying by increasing powers of 16? I highly encourage you to hit pause on this explainer right now, grab a piece of scrap paper, and genuinely test out your unpacking skills. Got your answer ready?
Okay, if you calculated 39,665, huge congratulations. You absolutely nailed it. You unpacked the code. You took 1 times 16 to the 0, F, which is 15, times 16 to the 1, A, which is 10, times 16 squared, and 9 times 16 cubed, and you summed them all up perfectly. Outstanding work.
And honestly, this just perfectly illustrates the massive, completely hidden mathematical architecture that is powering our everyday technology. Literally every pixel, every letter, every color on your screen right now relies on these exact translations happening seamlessly in the background. So I'll leave you with this provocative thought. How are these invisible math translations happening millions of times a second just to render the very text you are reading right now? The sheer scale of it is truly a marvel. Thank you so much for joining me on this Codebreakers journey through today's explainer, and keep exploring.